Welcome to episodes 5 of season 3 of the podcast that we call the Six Lessons Podcast. And so, in the Six Lessons Podcast, we've tried to give an overview of historical and the development of biomimetic dentistry, what it means, how it evolved from adhesive dentistry, how that's related to cosmetic dentistry or minimally invasive dentistry, how that differs from the traditional mechanically retained dentistry that everyone is taught in dental school still to this day. But this evolution is based on science, and unfortunately, if you're not a scientist, you really can't talk with authority on science. I was fortunate to be blessed with a father who was a scientist. And so he actually helped me understand what it meant to be a physicist or a chemist or even a historian that had a level of training that is referred to as a PhD, which is a doctor of philosophy. The idea of philosophy goes back 300 or 400 years before Christ, and it comes from a Greek tradition that the patron saint is named Aristotle. And his mentor was another proto-scientist named Plato. Now, Plato knew there are a lot of things you couldn't understand, but he wrote about these in a form called a dialogue. And a dialogue is a conversation, back and forth. Usually in these dialogues of Plato, he put his mentor Socrates as the person asking questions, and those questions would reveal how much his students, like Plato, knew or didn't know. So that's called the Socratic dialogue. But unfortunately, Socrates didn't know everything, didn't have every answer to every question, but he had important questions, like his most famous dialogue called The Republic said, "What is justice?" Well, here we are, 2,500 years later, still talking about those questions. Again, this is philosophy in its early stages. It evolves with the student of Plato, who is actually the beginning of what's called inductive reasoning, and that's Aristotle. So Aristotle was about above average, one of my favorite phrases on my tombstone. I tried to be above average. But Aristotle, he knew that his mentor didn't know everything. He couldn't answer very specifically, is there life after death? He couldn't understand how Plato could theorize a god that could create, but a god that could also destroy. There were a lot of what we call metaphysical questions, but Aristotle tried to focus on what we call physical questions. In other words, is there a breadth? Is there a depth? Is there a height to anything you're trying to describe? And many things, like the universe, it's very difficult to get to those dimensions, but Aristotle started to collect numbers. And so the collection of numbers where you say, okay, how many teeth do people have? This is a true story. He came to the conclusion that women had less teeth than men. Now, there were no dentists in those days. People lost teeth through a natural process. And giving birth to children causes problems in your physiology that would allow more women to lose more teeth. It's not justice. It's not the way we want it. But again, this evolution of early philosophy, asking questions, making deductions, that's called deductive science, and then making a observation, that's called inductive science. This is the kind of foundation that we would hope that the next generation of human beings would not neglect. But unfortunately, it's not easy to collect information and analyze it and then make deductions of those collections of data. Okay, so inductive reasoning and deductive reasoning work together in the scientific process. And every PhD, whether it's in history or whether it's in chemistry or physics, has the ability to come to conclusions that are different than past generations. Well, as I talk with my dad very superficially about these things, because, I'm just a kid, I just want to go out and go play basketball or go surfing or do the things that kids do in Southern California. The bottom line is my dad, when I had a question about physics, he didn't just give me the answer. He'd just say, "Why don't you look that up?" And my idea was, why don't you just give me the answers so I can pass my physics class and get on with my life? But, he was a wise man. And he also said, do your best. And in high school, my best was usually a B in science and math. Hey, that's above average. But whether you're talking about psychology, history, or basic science, this discussion or this dialogue back and forth has to be made because people can make mistakes. So, probably the most important phrase that I don't use enough is I might be wrong. Not my favorite phrase. And the other second important thing is you might be right. And so, if you have the attitude that a disagreement can be between two people that have the same goal, seeking the truth, seeking justice. Those are things that I believe that the biomimetic community has a good foundation in. But again, as we've talked to many times in this podcast, this is the science. This is the discussion. These are the collections of facts and data. And that dialogue back and forth when we're trying to collect data and then make deductions, what does this data mean? That's the scientific process. And of course, I've had many people hire me for many speeches that would like me to be able to tell them in an hour or 3 hours or 3 days what 30,000 hours of scientific research and discussion means. I'm trying my best. I'm doing my best to do this, but it's not easy. One theological proposition is that we come to earth. God wants us to learn things and wants us to make our decisions to try to help others. And that's a high ethical standard. It's not about just, making a lot of money or getting the most toys. It's about trying to feel fulfillment in helping others. And this is what the biomimetic community I am a part of does very well. I'm very proud to be a part of that. But now let's get into some real nitty gritty. 1999, I read this paper by Shoho. Now, again, 1999, I've been studying the literature for 4 years since I was introduced to published science by my first mentor, Ray Bertolotti. And so the evolution of my getting to understand that there are scientists, there is literature. And so I subscribed to 12 journals in the process of 12 months, 1998. Each of those journals cost something between $300 and $1,000 a year. These are journals that are not basically practice based, how to make more money to be a dentist, how to make your office prettier. They're not practical in the business aspect, but these were the scientific journals that usually are limited to faculty members at dental schools where the research can be done. But this article gave me some names that I was becoming familiar with. The lead author was Shono. Whenever you see a paper, the lead author is the one who's doing the work, usually related to getting a master's degree or a PhD degree. Now, the last author in a paper here we have Shono, Ogawa, Tereshita, Carvalho, Pashley, and Pashley. And so these are names that I'm reading in 1999. I don't really know very much about any of them. I did recognize the name Dave Pashley because the year before, in 1998, at the American Dental Association meeting, I bought this book, 1998, and this is called The Hybridization of Dental Hard Tissues. Dave Pashley, Nobu Nakabashi, 1998. I start reading that. The most important thing in that book are the last pages that contain 400 references. And so I knew that Dave Pashley was a major player in this idea of developing adhesive dental science. E.L. Pashley, I didn't recognize. I later learned that's Edna Pashley. Now, Edna is a pretty female name. So, Dave and Edna, I figured they were related. Sure enough, they were married. She became a dentist after they were married. And then she did research. Her specialty was more in pediatric dentistry. But the next name besides Edna Pashley and Dave Pashley was Ricardo Carvalho. Ricardo Carvalho is a dentist from Brazil who got associated with the research that was being done at Medical and Dental College of Georgia. And the Medical College of Georgia, that also had a dental school where Pashleys were at, brought in researchers from around the world, and they had the best in vitro testing, training, and execution of new products and new techniques in the United States. And they were associated with the best institution in Japan. which was Tokyo Medical and Dental in the 90s under the direction of Tagami. And Tagami obviously was the student with Inakoshi under Fusiyama, the father of adhesive dentistry. So this connection between Medical College of Georgia and TMDU over those 2 decades, which were really the golden age in the 90s and the 2000s of adhesive research that now we call biomimetic restorative practice, those two schools had everything. Other schools like Catholic University of Leuven, Belgium, started to catch up and started to do some things under the direction of their best student, Bart van Meerbeek, who is still active. We'll be speaking with him in Brazil for the second time this June. But as we get this paper, this is what it says. Regional measurements of dentin bonding in an array, resin dentin bonding in array. Now, nobody in dental school could understand anything from that title. And then we start seeing the graphs and the pictures. All of a sudden, he says, what are those graphs? That's a three-dimensional graph. These are short. These are tall. These are actually bond strengths. And it finds out that as they did this experiment, they tested different bonding system. That's one variable. In other words, a variable can be something that can be isolated, but you have to put it with the other variables in any procedure. And what they found out is that one bonding system was a dog. One bonding system was really good, but the biggest variable in this experiment was not the bonding system. The biggest variable that this one showed, this was a bad operator, this was a good operator. In other words, if you tell somebody to do something and they don't do it the right way, you get bad results. If you tell something and somebody and they do it the right way, you get good results. So when I read this paper many times, and I'm trying to isolate in 1999 the different areas that can increase bond strength and the different areas that can decrease bond strength. I isolated 18 areas that have been investigated and written about. But then when I read this paper in 99, all of a sudden, and I did know this, that I had to be my own best critic to be able to say, am I doing this right? Am I using caries detecting dye the right way? Am I using a bonding system the right way? Am I using a layering technique the right way or the best way, the optimal way? And all of these variables that I started to analyze eventually had 8 areas that could increase bond strength and 10 areas that could increase stress, which would decrease the bond strength. And so we called that the adhesive equation. This is the first paragraph of Gary Unterbrink and William Liebenberg's classic paper in 1999. You have to have more bonds than stresses for a long period of time to have a successful adhesive restoration that doesn't require retention form, resistance form. If the bonds are always higher than the stresses of polymerization and occlusion, which are the two main stresses, then that's going to keep functioning year after year after year. But again, that concept doesn't take into consideration that you need to have a way for quality control on the person who's actually using the caries detecting dye or using the bonding system or performing a layering technique or placing fiber. Okay, so here's one huge confounding variable. You, me, look in the mirror. Do I have good days? Do I have bad days? Well, yeah, we do. But we still have to understand that if we want the highest quality, we have to have a quality control. Now, let's go to 2005. So this is 6 years later. I'm now teaching my approach to advanced adhesive dentistry. And one of the main concepts in the 6 lessons approach was an understanding and an explanation of what C factor was. I was introduced to C factor by Ray Bertolotti, my first mentor, and I learned more about it in 2000 from my second mentor, Gary Unterbrink. And as I read the literature that came out of Holland, I identified this third university that had a major influence on understanding these products, whether they're adhesives or composites. This came out of the University of Amsterdam, which has the acronym ACTA, ACTA. And Carol Davidson, who was not a dentist but a physicist like my father, and had chemistry background, but he had basically in his physics training the ability to design machinery that could actually measure stresses and strains. A stress can cause a strain if the material moves, and these stresses and strains in a physics examination have practical application in engineering of airplanes or ships or cars or dental restorations. And so this team from ACTA started to interact with the teams from Georgia and the teams from Japan. But unfortunately, as is so often the case, if you're an expert in something, that's the thing you see the best. Well, by definition, an expert knows more about one thing. But let's say there's 6 things that you have to deal with when you're fixing a tooth. 3 of them increase bond strength and 3 of them decrease stresses. If you have 6 variables, each of those variables have areas that need to be investigated. And when we start talking about lesson 3, which is our lesson yesterday that we taught to the mastership group, we always have questions about bonding systems. And bonding systems have to first be tested. And in a test, as a scientist, you like to eliminate as many variables as possible so that the one variable they're changing, if you're changing bonding systems, then that can kind of be the indication of how they compare with each other. But you have to make everything else standard. So you try to have one confounding variable that's not confounding, that it's changed. We do it this way with this, we do it this way with this, we compare those experiments. Well, the idea of C factor in the 6 lessons approach, we put that in the 4th level of importance. In that lesson 4, we say you've got to understand caries because that totally can wipe out the bond that you're trying to establish if you put caries underneath your bonding system. How about cracks? Well, cracks and gaps give us symptoms and tell us if a restoration is connected or if the pulp is being infected either by decay or a fracture. Well, the third idea of bonding systems, this is the one that most dentists get really excited about. Because what's the best bonding system? If I could just use the best bonding system, then my adhesive dentistry would all work. And there are so many confounding variables that are not talked about. And when I discovered what's called the hierarchy of bondability, it was just based on tests of bonding to enamel, tests of bonding to superficial dentin, tests of bonding to deep dentin, tests of bonding to outer caries and inner caries. So there's 6 areas that the bonds and the bonding systems have to have some data to understand what they're bonding to and how they're bonding to it. And of course, the most important discovery after I discovered the hierarchy of bondability was that it takes time in these different areas to establish the maximum bond that's possible for that surface that you're bonding to. Oh my goodness. How do these numbers get into my head? How do we collect the inductive data, the data points that Aristotle would love, before we make the deductions of use this, use that, based on this data? Well, the tests themselves have to be considered a confounding variable. For example, a natural tooth that we're trying to mimic is moist. Where does the moisture come from? It comes from the pulp. The pulp is pumping out pulpal fluid, mostly water, but very important proteins that can establish a framework in collagen, and very important, I should say, organic materials like collagen proteins and inorganic minerals that can mineralize around the collagen that's in the dentin. Actually, a repair process for fracture or decay that happens in a vital tooth. Well, if you extract a tooth and then you test it, guess what? It's very different. It doesn't have that 20% water into the dentin. And so engineers know that a brittle material is more prone to fracture. A tough material, water makes dentin actually more resistant to fracture, but it's a very complex organ. And so most tests on teeth are on extracted teeth, and this gives us scientific information about some of the materials and some of the techniques. But a group out of Switzerland started to do something very ingenious, and that was they started to simulate pulpal fluid. In other words, the extracted tooth was now hooked up to a ringer bag like you see in a hospital, gravity forcing fluid into the pulp chamber, and the fluid is expressed through the dental tubules, and that's a better test. It's more like a natural tooth, so it's a more biomimetic testing setup. But the problem is it's more difficult to do that test. And the difficulty of setting up this hydration, only a few universities of the hundreds that try to do dental science have ever tackled that. A couple of universities out of Switzerland, and then the University of Tokyo Medical and Dental University started to do it. And the researchers were Nakajima, who established the in vitro bond test on a dry tooth, to inner caries and established that around 29, 30 megapascals, the same as the cohesive strength of enamel. Very important research in 99 that he published. But then he had a team under Tagami, but Nakajima is the main researcher, and then his assistant, who was working on her PhD, Monica Yamauchi, who I fortunate enough to know her. She's now at University of Indiana, where Dafina Dobrodoli is at. So Dafina knows Monica. She knows the science, how to do these tests. And the tests that you do to bond to a flat surface eliminate one variability, which is called C factor. So when you have a preparation that looks like a cup or a bowl, then you have a polymerization tug of war between the different surfaces that you're bonding to. So that's the information that came out of the 80s, 84, 87, out of Acta University. And so to eliminate this confounding variable, they would make flat preps on molars and then do bondings and then slice up 1 millimeter rods out of those bonded specimens and then pull the rods apart, and that's called a microtensile bond test, developed by Hidehiko Sano in 1994. It's much more difficult than what's called the shear test, which was developed 10 years before, but had different results because the stress accumulation was different when you had this shear failure, push till failure done on the standard materials testing machine that's called an Instron machine. Anyway, the development of going from a large macro shear test to a small microtensile test. There's a whole history on that, but you have to learn how to do that. For example, Dafina Dobrodoli, one of our mentors, has learned how to do that both in Europe and in the United States. But to slice something 1 millimeter, of course, that's the thickness of two of your fingernails, right? That's not a big slice. You got a diamond that's spinning around that could cut your finger off. And then all of a sudden, you have to slice these little pieces of bonded tooth structure in 1 millimeter, 1 millimeter, and then turn it the other way. And you have this slab that now has to be cut into rods so that you can get 10 data points off of a molar instead of 4 or 5 data points off for a molar. The original was the slab technique, and then it got modified to the rod technique. But all of these, to learn how to do this without cutting your finger, and do it right, you have to, be able to follow directions and then understand your data, how it gets accumulated. And then you have to average your data, and then you have to see if there's statistical differences. And statistics is a whole area of science that can make you crazy, but in simplification, statistics can help you not make big mistakes. But when they tested a fluid pulpal simulation in TMDU, what they found out that the bond strength to the sound dentin on these flat surfaces was the same as the bond strength to carious flat surface. Now, earlier research in 2000 on extracted teeth said that the bond strength to sound dentin should have been much higher, in the 50 megapascal range, which was the tensile strength of the DEJ. And so when I read this paper in 2006, I analyzed it and looked at it, and I found the confounding variable, or the design of the study, that was the flaw. What was that? A tooth at the DEJ is shaped like this. Every dentist should understand what I'm saying, okay? In other words, you've got cusps, you got pulp horns, and then you have grooves, and then you have an area in the pulp that is shaped like this. If you cut a molar across, you are finding a confounding variable that you are now exposing superficial dentin, intermediate dentin, and deep dentin in those preparations. So it has to be averaged. And deep dentin has 3 times more fluid than superficial dentin. Superficial dentin is more like enamel. Deep dentin is more like pulp tissue because the orifices of every tubule is 3 times as wide next to the pulp where the odontoblast lives as it is in the odontoblastic process that almost reaches the DEJ, where there's massive amounts of peritubular dentin near the DEJ, almost no peritubular dentin next to the pulp. So the actual anatomy of the tooth has to be understood in great detail. The Urabi's 2000 paper compared to this paper from Nakajima in 2006, these are both good people. The teams are both good teams. They're all doing something, and they tell you exactly what they did. But when I read the paper in 2006, I said, what? They made a mistake. They're averaging in superficial bond strengths, which will be in the 50 range, and deep bond strengths that will be in the 30 range or lower. And all of a sudden, that average gives them that idea that you get a bond strength of around the same as intercaries dentin, and the intercaries dentin always has a product in it that is called whitlockite. And of course, if you're listening to this lecture and you've taken the 6 lessons training, you know what whitlockite is. Why? Because we've referenced the many articles and books of the founding of adhesive dentistry, Takao Fusiyama, who identified whitlockite as the tri-beta calcium mineralization that forms after the peritubular dentin is demineralized from acidic action of decay. And I know that, probably most of you are switching this off and trying to figure out something that's more fun to do today. But again, this may be my last lecture, so I can't help myself. I know that this is important, and I know that if you try to break down what I'm saying, you will come to some very similar conclusions. Okay, let's take the last paper. This is the last one for today. So this one was 2005, the year before the simulated pulpal pressure paper was published by Nakajima and Yamauchi that did not recognize the hierarchy of bondability that was introduced in their preparations. Well, this paper, when I read it in 2005, I did not know personally Junji Tagami. Obviously, I know him now. We've spoken at conferences together many times. But they were trying to counter the arguments that were being made out of Europe, mostly under the direction of the European influence from Amsterdam, investigating C factor. And the investigations of C factor that were done in Germany gave very specific numbers on the reduction of bond strength with C factor increases. So the ratio of bonded and unbonded surfaces did get proven by Rulin Frankenberger and his team, led by a Russian researcher, Serge Nikolenko. Other research out of Turkey, Sema Belli and her team, had the same conclusions, but they introduced other variables such as the action of matrix metalloproteinase action on bonding systems. That was also in 2005. But this paper made a model made out of plastic that varied the C factor form and came to the conclusion, based on this test, that there was no significant difference in bond strength among the 5 different cavity forms. It was concluded that the difference of cavity forms has little effect on adhesion to the cavity floor when using light cured composites. When I read this once, read it twice, read it 3 times, I wrote my conclusions on the back of the paper. Again, 2005, I've been teaching 6 lessons for 2 years. I believe I've got it all figured out. So far, we haven't had any failures after 2 years of teaching other dentists. But this is what I said. I said, the stress that they're measuring is one of 3 places that stress in a natural tooth can be manifest. 1, in the tooth, 2, in the bond hybrid layer, or 3, in the composite. In this experiment with the ABS plastic blocks that they were put into shapes, the ABS bond was strong immediately, and the higher stress in the composite and the higher C factor was not measured in the hybrid layer, but in the strain of the plastic blocks, which wasn't measured. And, who am I in 2005? I'm not the father of biomimetic dentistry, or the leading researcher according to the Chinese AI app, which I don't have, but, occasionally it says I'm right up there. Well, in 2005, I only had a few groups, maybe 20 doctors that had been trained. And I took my best student, Arnaud Note, and brought him to my house into the basement. And I read that article to him. And I said, "So, what do you think about this?" Now, he's just fixing teeth using the 6 lessons. For 2 years, he's had no problems, except he left some cracks into dentin before he had a microscope and before he had more confidence that that was important. He tried to bond over cracks for 4 years, but he had to replace all those vertical cracks. The horizontal cracks he got away with, and we explained that in lesson 2. But after 2 years, in 2005, I'm talking with Arnaud. I said, "Arnaud, there's a problem with this experiment. There is a variable in this experiment that they have removed, but it's never removed in a dental indication until you get a resin coating." And with that hint, then he said, "Oh, they're not bonding to a tooth." So this in vitro experiment was not with an extracted tooth, but the shape of the cavity was formed into a plastic tooth. And so when they measured the bond strengths were all the same because there is no hierarchy of bondability, meaning no decrease of the weaker polymerized bonds at the expense and giving more strength to the higher mineralized portions of the tooth. So there was no polymerization dynamics. There was no movement of the composite that would weaken the hybrid layers. So this is called neutralization of the hierarchy of bondability. And that happens in a biomimetic restoration as soon as you have a resin coating. And then if you want to decrease that second area that the stress can be manifest, which is the strain of the tooth structure, then you can use an indirect or a semi-direct technique or a stress-reduced direct technique. Those are the 3 ways to eliminate the strain on the tooth. Well, when I find these mistakes, but if I have an answer and I understand why those mistakes were made and it fits in with the larger deductive conclusions about how to make it work in a more biomimetic situation, meaning a natural tooth, all of these things I have to wake up every day and say, okay, what do I know today? What do I know tomorrow? Last night we had a great lecture by one of our mentors, Dafina Dobrodoli. She introduced a paper that's hot off the press from Okayama University by Kumiko Yoshihara, and she happens to be the best chemist who's also a dentist in the world that I know of personally, has a PhD level knowledge of chemistry where she can do original research, and she understands how ionic bonding in the calcium that's taken out of a self-etched situation by a higher pH, a less acidic material like 10 MDP, how this calcium can be put into what's called a nanolayer that acts like a filler and actually increases the modulus of elasticity on a bond to a natural tooth. And that was done on a 10-year follow-up on an extracted tooth. And that piece of paper, that research, how many people in the world will find that? I wouldn't have found it unless I had Dafina, working with us and sharing that with us. And, she has skills to recognize what it is to have a master's degree in science, what it is to have a PhD in dental science. Is it an easy life? No. Does it make you rich and famous? No. But if I ever talk to somebody about nano layering with self-etch adhesives, I am always going to mention the names of Van Meerbeek and his best students, Yoshida, and his best student, Yoshihara. This knowledge and how this works in this dialogue across continents, I mean, as long as we can, read English and have somebody that we can talk to it about, then these answers get narrower and narrower and more science, and these facts become the sweetest dream that labor can know. A quote from my mother's favorite poet, Robert Frost. Well, we went a little longer today than usual. But like I say, it might be my last lecture. But until next time, get bonded, stay bonded.